Welcome to homework.
So beams of light always have different wavelengths, and one of them that you always come across is the X-ray. A lot of times, people are familiar with the X-ray from hospital requirements when you want to take like chest X-rays, or if you go to the dentist and you want to take X-rays with your teeth. So in this case, we have a beam of light, and its wavelength, we're going to call that lambda. So we have a beam of light, and the wavelength lambda is equivalent to A, and it does follow what we call the Bragg law of diffraction. Bragg law of diffraction. And there's a crystal. We're just going to have a crystal right there, or alternatively, we can have it as a straight line, but we do know it's a crystal. And it so happens that the wavelength A, this wavelength, undergoes the first order of reflection. In this instance, its angle of incidence happens to be that angle happens to be 23 degrees. And of course, there's bending that's going to happen once it goes through the crystal. And then in the second instance, we still have another type of X-ray, but this time it goes through. Well, this angle right here should be 23, so this should be a little bit smaller than that. This angle is 23, so it's somewhere right there. You could put the angle right there. That's 23, and then the other one is 60. So this second angle right here is 60. This is still the crystal. Think about it as a crystal that takes in some kind of reflection. So there's reflection going on. And of course, first order reflection, lights, things are bouncing back. You want to think of it that way. There's going to be diffraction and reflection going on based on the Bragg law of diffraction. The wavelength of the second case, lambda, is 97 PM, and it undergoes third order reflection. This one undergoes first order reflection. So those are the two types of reflection that we're seeing in this particular problem. And we have two beams of light, and they both belong to the same family of reflecting planes. In part A, we want to find the interplanar spacing. And then in part B, we want to find the wavelength of A. So they never gave us the wavelength of A. We want to find that. And we also want to find the interplanar spacing. We're going to jump onto the next page. And in part A, the Bragg condition. We have the Bragg condition in part A, and it's given by 2D sine theta equals to m lambda. For m equals to 1, first order, the angle of incidence, as you can recall from the previous page, is theta equals to 23 degrees. That's the angle of incidence. Theta equals to theta happens to be 23 degrees. And then the wavelength, we're going to call it lambda A. That's the wavelength. We don't know what it is, but we're trying to find it. In the other case, the second case, if you go back, this happens to be the second case. So for m equals to 3, theta is 60, and lambda is 97 p.m. 97 p.m. That's the lambda. Of course, the first part is we want to compute, as you can see, the interplanar spacing. So interplanar spacing, and that's based on the second case. Second case, we know 2D sine theta equals to m lambda, so 2 d sine theta, theta is 60, m is 3 for the second case, and 97 p.m. for the lambda, so d equals to 291 p.m. of 1.732. So the interplanar spacing d is the same as approximately 1.68 times 10 to the 2 p.m. That's the interplanar spacing. We've used the second case since it has all the information we need. We're going to jump onto the next page. This time in part B, we're applying the first equation. We have 2d sine theta equals to m lambda, and we already know what d is. So d happens to be 1.68 times 10 to the 2 p.m. We found that d was the interplanar spacing in the previous part. And then sine of theta is 23 degrees. M is 1, and we want to find lambda, so lambda becomes equivalent to or lambda A, if you want to call it that, just becomes equivalent to 1.68 times 10 to the 2 p.m. Sine of 23, and so A becomes the same as 1.31 times 10 to the 2 p.m. So once again, this problem had two parts. In the first section, we had the diagrams. We wanted to find out, we're given incident angles at 23 and 60, and then reflection takes place in both cases. One of them is first order, m equals to 1, and then we have third order. We're supposed to get the interplanar spacing and the wavelength of part A, this one right here. We use the second condition where we're given all the requirements and the Bragg condition. Plug in and get that the interplanar spacing is 1.68 times 10 to the 2 p.m. And then in the last case, we use the value of interplanar spacing to find lambda based on the Bragg condition. So hope you enjoyed the problem. Feel free to send any questions or comments, and have a wonderful day.